So I'll start on this slide here. Stress corrosion cracking. So I put a table here with some numbers on, just to give you an idea of how we might quantify this. So in particular, we have some alloys, we have some steels, we have some nickel alloys, some bronzes, aluminium, zinc, and titanium, vanadium. I'd say a bit more about those in a moment. So we have the alloy, we call it an alloy. And we have the fracture toughness, the KIC, or K1C, is the fracture toughness. It's a numerical value for, if you like, how strong the material is. So the bigger the number, the tougher the material is. And the smaller the number, the weaker it is. That's in a nutshell what the KIC or the K1C is. I put a bit of a definition down here. Fracture toughness is a measure of a given material's resistance to crack growth. In other words, the bigger the number, the more resistant it is to cracking. So clearly that's important when we talk about stress corrosion cracking. So this is a quantification of how good the metal might actually be. But the value does depend on the environment it's in. So in air, it might have these values, but in a stress corrosion environment, which are these solutions here, it could be much lower value. So let's take a couple of examples. So let's take, this is a 13% chromium steel. So it's a stainless steel, in other words. And in air, it has a value of 60. And but in 3% sodium chloride solution, that value of 60 goes down to a value of 12. So it's much lower. So this is the reason why stainless steel should be used with caution, let's put it like that, when exposed to seawater. So this is more or less a seawater solution. 3.5% sodium chloride would be a seawater solution, or more or less the strength of salt in seawater. And when you put the steel into this environment, then its K1C value drops from being 60 down to being just 12. So that's why stainless steel is susceptible to stress corrosion cracking in a chloride environment. It's normally the thing to avoid with stainless steel. Next down we have, this is a high strength steel. It's 18% chromium and 8% nickel. The balance is iron. So it's a chromium nickel iron alloy. And it starts off with a value of 200. But if you put that into magnesium chloride at 42% by weight, it drops down to a value of 10. There's a lot less. Now let's take the next one. This is copper zinc alloy. This is a brass, in other words, 30% zinc. Copper zinc is called brass, or Messing in German. And it's 30%, fairly typical. Again, a very high value, 200. But if you put it into ammonium hydroxide solution at PA7, it drops down to 1. And that's not surprising, because anything containing copper in an ammonium solution is asking for trouble because it reacts. So it's hardly surprising it drops down to a value of 1. So you should never do that. You shouldn't put this alloy in contact with ammonium hydroxide, even though it's at a neutral pH. Next one on the list is an aluminium magnesium zinc alloy. And this is 3% magnesium and 7% zinc. The balance is aluminium. And it has a fairly low value to start with, but it does not like being in halides. A halide is a solution of chlorine or fluorine or bromine, for example. The halides, if you recall, in the periodic table are on the far right-hand side next to the noble gases. So we wouldn't want to put this in contact with sodium chloride, for example, because that chloride is a halide. So it drops from 25 down to 5. Not quite as catastrophic as these two, but nonetheless, it still goes down. And the final one is titanium, aluminium, vanadium. 6% aluminium and 1% vanadium. And it starts with a value of 60. But if you put that in contact with 0.6 molar potassium chloride, it goes down to a value of 20. So what we're saying is that for any given alloy, if you really want to know something about how strong it might be in the environment, you need to know the K1C values, not only in air that you look them up, you need to know what they are in the environment as well, because it's going to be very different. And because people don't know this, they often make the mistake of putting what they think is a high tensile material into an environment where it's going to react and it becomes low strength, and they don't realize it. And this gives rise to failure. And this mistake is often made at the design stage, where somebody's designing something quite complicated, and the mechanical engineer might not be trained in corrosion and might not know this, or might not be trained in material science either, and might not know this. This is why it's so important for you to learn these things, because you'll probably get jobs in as engineers at some point, and it's very useful to know these sort of numbers and this level of information. And just to emphasize the fact that stress corrosion cracking occurs a lot in brass, and here is an example. So now I'm going to move on a little bit to how we might actually test materials. So we've learned something about stress corrosion cracking. We know the basics now. We know the basics of hydrogen embrittlement. Now let's look at how we might actually test some materials to see how we can, first of all, measure the effects of stress corrosion cracking, and how we can measure the effects of hydrogen embrittlement, and how we can analyze the materials to learn more about it. And very often what we do is we make a specimen which is made out of a metal. This happens to be a piece of sheet metal, and we cut out a groove in the middle, this shape. So we narrow it down, we make it thin in the middle and thick at the end. And these two holes here represent where we attach it to a machine to stretch the material. So we pull the sample in both directions, left and right. Because we thinned it down deliberately with this profile, then most of the force we're applying is in the middle, somewhere between here and here. And if you pull it for long enough, it will break, it will fail somewhere in the middle between this point and this point. And if we plot a graph, this is showing the stress versus time. Then if we pull it at a fixed stress over some hours, after 50 hours, then it starts to break. We start to form a crack even, and the stress goes down. At this point here, the sample breaks completely. So from this point here to this point here, we're forming the crack. What's actually happening is that we're stretching the material and it's getting thinner. And when it gets thinner, the stress actually starts to go down, because the material becomes very ductile. It starts to pull apart. And when it breaks completely, there is no force left on the material. The two ends are completely free. So you need to understand, as you start to stretch the material, as it becomes more ductile, if you like, and we've started to form the crack, then the stress actually goes down until we reach the point where we have failure and it breaks and there is no stress anymore. It's gone down to zero. And that this particular case has taken 40 hours to get to that point. So here's some ways of testing materials. I've got two in this particular overhead. On the left-hand side, we have something called a constant load test. And on the right-hand side, B, we have something called a slow strain rate method. And these are two laboratory methods for testing a material to see if it's susceptible to stress corrosion cracking, and if it's even susceptible to hydrogen embrittlement. And normally what we do is we take the specimen, we put it inside a container, it says specimen there. And this is so the first method, the constant load test, is a loop going all the way around of very strong material. And we have a bolt going through to which the specimen is connected. And we tighten the nuts up either side of the specimen chamber, and we put a force on it. And we measure the force with a force meter, usually with a load gauge, and we just leave it over a long period of time. And if we leave it long enough, the sample will break. And that length of time might be several days. It could be several weeks, in fact. So a constant load test will give a result. But the problem with this test is we don't know how long to wait. It could take weeks for it to break, or it could happen in a few days, depending on what material it is. So that's this test. The one on the right-hand side, the B test, is called the slow strain rate method. And what we do here is, instead of putting a constant load on it, we increase the load all the time until eventually the material does break. But we need to put it into a crosshead testing machine like this to make it do that. And the great advantage of the slow strain rate method is it always gives a result very quickly, typically between 1 and 2 days. You don't have to wait weeks like you do in this case. So this is a very much faster method of testing than this method is, but it's more sophisticated. Here's a photograph of an actual proof ring. And I should point out that when we're doing these kind of testings, there are standards. This is a NACE test standard, TM0198, is a specific test procedure or protocol, which would have to follow to do the actual test. And this is the real thing. And what I showed you before is just a drawing of it, but this is the real thing. And here's a little glass chamber, which contains the electrolyte and the aggressive environment to which the sample is exposed. You can just see what looks like a rod in between. And here's a person tightening it up and measuring the force on this gauge here. And when they've tightened it up, the force or the gauge, the load remains constant throughout the whole test. It doesn't change. But the sample is exposed to that constant force all the time until eventually the corrosion and the cracks appear and the sample will eventually break. And what does the sample look like? Well, typically we take a metal which is usually round in cross section, as you can see here. And what we normally do is we thin it down in the middle with a profile. It has a certain radius here and a certain diameter here and a certain length here. So it says 25.4. That represents the distance between this point here and this point here. This surface here is like a rectangle. The faces are parallel to each other. And this is called the gauge length. And this is where we're going to get a failure. It's guaranteed to fail between this point here and this point here. I'm not quite sure where, but it will be certainly between those 2 points. And that's called the gauge length, which has a distance of 25.4 millimeters. The diameter in the gauge length is 6.4 millimeters. And here we have a radius of 15 millimeters. That's a radius there, and another one here. And then we come to a much bigger diameter here. And if you look in this cross section here, the diameter says 6.4 there. In cross section, it's this dotted line here. This is 6.4. And the outer diameter will be much more than that. And so then, therefore, because this is much thicker, obviously we're going to break the sample in the thin part. That's why we thin it down to make sure that does happen. And then we pull the sample in our test rig to stretch it, to put the tensile force onto it, to make it break somewhere in the gauge length. Here's a photograph of one that's been made. When I finish the lecture, I'll show you some of my own, by the way, but I'll do that in a moment. And this is the testing machine itself. So on the right-hand side, we've got the sample made according to the dimensions I've just described to you. And here's the testing machine. And this part here and this part here is called a crosshead. This is the top crosshead and this is the bottom crosshead. And we have these vertical pillars. And the way this particular system works is that the top crosshead moves up and down on these pillars. And we have a load gauge here which measures the force. And in the box here, we have a gear mechanism and a hydraulic drive, which in this case pulls the crossheads apart. If you want to stretch the material in this direction, we need to make this go up relative to this. So we're pulling the specimen. And this is the control computer for everything. So it says corrosion-induced slow strain rate test system. So this is designed to do the slow strain rate method. This is looking at it slightly differently. Here we have a rectangular specimen, and these 2 large-looking objects are called grips, and they're hydraulically driven. And when this is in operation, we press the start button and use a computer here, then the top grip moves up relative to the bottom grip. So either this can move down and this is stationary, or this one's stationary and this one moves up, but the effect is the same. We're stretching the material, we're pulling it apart. And it's very important that the grips are much bigger than the specimen, meaning that they have to be stiff, because what we don't want is to get any flexure or bending of the grip itself or the machine. We want all the stretching and all the tensile force to be applied only to the specimen and not to everything else. Otherwise, we won't get any sensible results from the test. So here's an example which has been broken. In a moment, I'll show you my own. But so this is the top grip and this is the bottom grip. And this thing here is called the clip gauge, which is measuring the distance between them. So it's measuring what we call the elongation. So the idea is that we pull them apart. Let's say, for example, the top grip is moving up and the bottom grip is moving down. We're stretching the sample. So the distance between this point here and this point here is increasing all the time as we pull the sample apart. So we're stretching it. We're increasing what's called the elongation. And when we do that, the crack is starting to form here. And because this material has some ductility in it, you can see its necking has become thinner in the middle than the rest of it. So if you look here, you'll see a slow decrease in the diameter, and that diameter decreases more rapidly as we come to the point where it's broken. And you can see it more obviously here. You get this sort of bottleneck effect. This is called a bottleneck because it looks like the neck of a bottle. And when the bottleneck starts to form, you can guarantee it's going to fail there. Once this happens, it's never going to fail up here or down here. You can be sure of that. It will always fail here, right between the gauges. This is the elongation, the device that measures the elongation. It's called a clip gauge. Here's the top clip and here's the bottom clip. And there's some electronics made by a company called Instron. That's the company that makes it. If their emblems showing two people pulling a piece of rope apart. And here's the cable going off to the computer. And if we take this material and look at them under the electron microscope from the top view, then that's what these are. These are photographs looking down on the fracture surface. If you take these out and put them in the electron microscope afterwards, then it looks like this. Here's the other one. So you can see the thinning down effect. So the diameter where it's broken is much thinner than the diameter of the rest of the specimen. And it's more obvious here. You've got different types of fracture here. You can see a different fracture pattern here than you can here. So it's a combination of ductile fracture and brittle fracture, actually. If you want to do the stress corrosion cracking experiment using a corrosion medium, you need to put the sample inside a container shown here, which is filled with the corrosion medium shown here with the arrow. And these are the grips I just showed you. And here's the tensile sample here. And this is the machine doing it. And here you've got the dimensions of the sample, just like I said a minute ago. So the gauge diameter is 6 millimeters. And the rest of the diameter is 10 millimeters. And the gauge length in this case is 32 millimeters. And the total length is 100 millimeters. And you can simplify the diagram by showing it like this. This is a load cell. Load cells, by the way, measure force in newtons. So this is like a balance upside down that's measuring directly the force in newtons. These are the two grips, the bottom grip and the top grip. And here's a specimen held between them. In this particular case, the bottom crosshead is stationary and the top crosshead moves up and down against this screw thread. This is actually called a ball screw. So this is the moving crosshead. It goes, if you're going to do a tensile test, it always moves up. But sometimes you might want to do a compression test, in which case it goes down. But in stress corrosion cracking, you're always going to be putting a tensile force on. So you're going to move the crosshead up relative to the bottom one, which is stationary. And this is a slow strain rate test method described in ISO standard 7539-7. So you have to get used to these numbers. And if you become an expert, you'll just simply refer to that standard if that's what you're following. And here's the sample again. Here's the clip-on extensometer that's measuring the stretching of the sample. In other words, what we call the elongation. And here I've specifically marked the gauge length. The gauge length is quite literally the distance between the two indicators on the clip extensometer. So we have a top monitor and a lower monitor. They're usually metal forks that just touch the surface of the sample and they move with the sample. So if the sample stretches, this will stretch with it. In fact, it'll bend, to be more precise. And it'll measure very accurately the elongation In other words, how much we stretch the sample by. Let's say we stretched it by 10%, then that 10% will get picked up by the gauge, the extensometer, and be fed by an electrical signal to the control circuit. And eventually you get this. Now, hopefully you've seen this before in the other half of the class, so I'm not going to explain all the details of it, but this is a stress-strain curve. So the elongation is along here. So strain is the same thing as elongation. We're stretching the sample because it's a tensile test. So we start here and we move along this way. So let's say this point here where it breaks is 10% extension of the original length. So if you had 100 millimeters, then we've increased it by 10 millimeters, 10%. Here we have the force per square meter. In other words, the stress. The stress is force per unit area. Hopefully you already know that. So if you have a metal and you start stretching it, then the first thing that's going to happen is you're going to go through the elastic part. This is where the Young's modulus is relevant. So if you pull the sample, in other words, Hooke's law is valid. If you stretch the sample, the stress-strain relationship is linear. And the slope of this is the Young's modulus. And if we take away the stress, it'll go back to the original position and there won't be any plastic deformation or permanent set. In other words, we haven't destroyed the sample. But if we go too far, then what will happen is the specimen, if it's ductile, will start to yield and it'll start to bend over like this. And this is the yield point here. It'll bend over like this. And if you take the stress off at this point here, it won't go back to that point. It'll come down here like this. Whoops, I don't like this, like that. And there'll be a point there. This distance from here to here is called the permanent set or the deformation. And therefore, you probably destroyed the sample. It probably won't do what you want it to do anymore. Certainly, if it was a spring, it would be useless. So therefore, but in the case of stress corrosion cracking, we deliberately, on purpose, pull the sample all the way up until we reach the maximum, the ultimate tensile strength. And then we start, at this point here, the sample starts to neck. We got that necking effect called the bottleneck. It starts to thin down. And now the stress starts to go down. At this point here, it breaks. And this is the fracture point. And that strength there, the value here, the stress here, is the fracture strength. So when we do the slow strain weight method, we're measuring this point here very precisely. And this is what we want to know. What did you want to know? This point, and we want to know this point. We're not so interested in all of this because we're deliberately breaking the sample because we want to see when it's going to fail. That's the whole point of the slow strain rate method. So something else to understand is that these are metals, these are actually steels. Steels come in different types. We have high carbon steel or very strong, what we call high strength steel. And these contain quite a lot of carbon. And then we have medium strength steel. And then we have low strength steel. So low strength steel or low carbon steel is the most ductile. It's the kind of steel you might make the bodywork of your car out of, for example. Whereas the medium strength steel might be used to make a bolt. And the high strength steel might be used to make a very precise fitting, or it might be used to make a tool, or something that needs to be very strong. But there's a trade-off between strength and fracture toughness and the ability to elongate the specimen. So if we take the low carbon steel, that's this one here, then when we do the stress strain curve, there's a Young's modulus part and it'll go through this shape. The maximum ultimate strength is not so high because it's a low carbon steel, but you can stretch it, it'll deform a lot because it's very ductile. So it won't break until you've extended it by a significant amount. Let's say it was 15% at that point there, and then it would break. Now let's take the next grade up, the medium carbon steel. It says the toughest here. So again, it's the same story, but this time we go up to a higher point here and almost a much higher yield strength here. So the maximum ultimate strength is much higher than we had before, but it breaks sooner. So let's say this breaks at 10%. This is 15%. Let's say that's at 10%. So this one, the trade-off now is you can't stretch it so much before it breaks. So this is going to be more susceptible to stress corrosion cracking than this one is. Now we go to the high carbon steel. So again, we go at the same curve. You see the initial part is the same in each case. They almost have the same Young's modulus in actual fact. Go up here, but this time we go to a much higher, but it's broken already here. Let's say this is at 5% and it's broken already, it's fractured here. So this one, you can hardly stretch it at all compared to the most ductile ones. You see the difference between the elongation here before it breaks and the elongation here before this one breaks. So therefore, in terms of susceptibility to stress corrosion cracking, this one's the safest. This one is somewhere in between, and this one's really dangerous. You want to be very careful when using a high carbon steel in an environment where you could get stress corrosion cracking, because this probably is going to fail on you. This one might do eventually, and this one's probably never going to fail on you. So you see that now why it's so important to measure with this apparatus, this kind of data, to be able to see something like this. You need to know something about the material science itself to make a decision. So you need to know what kind of steel you've got in this particular example. And then how do we do the rest of it? So we need to put the environment in. It's no good just stretching the material in air. That's not going to tell us what we want. What we actually want to know is how susceptible it is to stress corrosion cracking when we have a corrosive environment present. So now what we need to do is build a box, what we call a cell, all the way around the specimen, shown here in this diagram. It's a container which is quite wide but not very thick, and the whole thing fits inside between the two grips. So one grip will be up here and the other grip's down here, and we pull the specimen apart that's inside the container, so we have to seal it in somehow. If you look carefully in the design, you've got O-ring seals, one here and another O-ring seal here and here. Otherwise the liquid will drain out. And if you look carefully, you'll see the specimen has a screw thread on it, which screws into the grips to keep it tight. This could be a plastic container, and we put the liquid inside here, and we need a reference electrode. This is a saturated calomel electrode like we used before, so you know this one. And here we have the auxiliary electrode. And here we have the potentiostat. This is one made by ACM, as it happens. And the auxiliary electrode is made of platinum. And then what we do is we can apply electrochemistry to this. We can apply, for example, cathodic protection, like we saw last week. And now we can see the effect of cathodic protection on the ability of the material to withstand stress corrosion cracking, because we apply the CP, the cathodic protection, to the specimen. At the same time, we're stretching it in the testing rig. And we're going to do the slow strain rate method, so we can ensure this will fail within about 1 to 2 days, maybe even just a few hours, depending on how fast we pull the specimen. So now let's just go on and say something about stress corrosion cracking in terms of cathodic protection. So now we're bringing the electrochemistry into the argument, as well as all the mechanical and the microstructural arguments. Now, you're well familiar now, hopefully, with the Tafel plot. So we have a Tafel plot that's been obtained in some liquid. It doesn't matter at the moment what it is, but let's say that it's a neutral pH. Let's say it's seawater, for example. And let's say we have a high tensile steel that we're testing to see how susceptible it is to stress corrosion cracking. And here we have the free corrosion potential. It's slightly less than 0.8 of a volt. And if we polarize in this direction, we're going in the cathodic direction. And if we polarize in this direction, we're going into the anodic direction. But if we are applying cathodic protection, which is what we do want to do, then we're going to polarize it in this direction only, in the cathodic direction. And now we need to understand the reactions that are going to take place when we do that. Well, we already know that when we talk about rust, the main cathodic reaction is this one, where you have oxygen reduction and it forms water. If you follow the arrow, that occurs in the early part of the curve, fairly close to the E-core value. So if we have this free corroding and we don't really apply much of a potential at all, let's say minus 0.7 of a volt, let's say that point there, then this reaction is going to occur. And as long as we have oxygen present, that's probably the only reaction that will occur. But unfortunately, if we consume all the oxygen, which might eventually happen, this reaction will stop. And then this reaction takes over. And this is the reaction which gives hydrogen evolution. This is the one we want to avoid happening. But it becomes unavoidable if this one doesn't happen anymore. Or worse still, I use that word worse because it makes stress corrosion cracking more likely to happen. If we drive the potential further down to, say, this point here, and now we're at about 0.75 of a volt, let's say, and we go even more down here. Let's say we go down to minus 1 volt, which is down here. And minus 1 volt, the point where I've got the cursor now, this is the only reaction you need to worry about. And we're going to get hydrogen evolution for certain. So for a high tensile steel bolt, for example, or a material that's made out of high tensile steel, this is bad news, because if we do cathodic protection, we think we're preventing corrosion from happening, which we are doing. Unfortunately, because we're driving the sample in the cathodic direction, we're generating hydrogen. So we may not get any dissolution of the iron. So we stop the iron from dissolving. That's not the problem. There's no problem with iron dissolving. The problem is the hydrogen itself is going to perform, it's going to get absorbed by the metal. We're going to get hydrogen embrittlement and it's going to crack. And we're going to change the ductility. Well, actually, we're going to reduce the ductility, to be precise. So now if you look at this stress strain curve we just looked at a minute ago, as a function of applied potential, we get a whole family of curves. So imagine that this is a high tensile steel sample, and we've made our specimen. And let's say we test it in air without the corrosion environment. Then that's the black dotted line. So here's the Young's modulus part. Here we are, we're going through the maximum strength here. And now we're starting to, it's quite ductile, you can see. So we can start to stretch the material, and the elongation, here's the strain rate percentage. So that, let's say that's equivalent to 14% elongation at this point here. So as we come down, the material is quite ductile because we're not in a corrosion environment at the moment, we're just in plain air. It comes down quite a lot. So it's really necking, it's getting quite thin. A bottleneck is occurring at this point here, it breaks about 14, somewhere between 14 and 15%. Now let's put the environment present. We've gone back to setting this experiment up. Now we put the cell in, we've got the specimen going, and now we just apply, we're not applying any potential at all, just to the free corrosion potential, which on our IV curve, we're at this point here. Now we do the slow strain rate method at this point. There. Now we're following the red line. But not much is happening here. The first thing we notice is that we go to a higher maximum than we had previously. So we've actually increased the strength of the material already. And we find that it elongates, but nowhere near as much as it did before. So the very presence of the liquid, even though we're at the free corrosion potential, has already made an impact on the material's microstructure. We're already seeing an effect. Even though we're at the core value, there's still an effect, and we're causing the ultimate strength to increase from this value here to that value there, but we're making it break sooner. So now the elongation is around 10%, whereas before it was just over 14%. It's quite a big difference. Now, let's move down the IV curve and go to this point here, minus 0.77 millivolts. That's, let me see, 77. So it doesn't correspond exactly to this one. I'll carry on talking. Let's say we're minus 0.77 millivolts. Then it follows the yellow curve. And it breaks here at this point here at about 8%. Now let's increase to minus 970 millivolts. That's this point here. We're operating at this point here now. There. Then we find that we follow the blue line here. Now we find it's breaking at about 7%. And now we're going, the third one is at minus 870. That's this point here. And it breaks at around 6%. So what's going on here is that as we apply the cathodic potential, we're making the material less ductile. It's breaking with less percentage strain, and we are increasing the ultimate strength, and we're making the material more brittle, and we're making it crack with less elongation. And if we take the sample after we've broken it and look at it under the electron microscope, it'll look something like this. And the red line here is indicating where we have something called ductile fracture. So all of the lines, all the microstructure in the red region, it's like a country in a map, this is ductile fracture. And everything around here, which is most of it, is brittle fracture. And you can see some cracks here, you can see some cracks here and here and here. And if you look carefully, you see cracks here. These are cracks caused by hydrogen embrittlement in the sample. And if you look at the higher magnification, these are the grains, and you can see the cracks in the grains. If you look carefully here, I'm just drawing the cursor around where I can see the cracks myself. They're all over the surface. There, cracks everywhere. And that's most of the surface. The only bit that was not affected by the hydrogen was in the red region here, which is that island here. Most of it's been affected.